Hello and welcome to Electromagnetics 1. Dr. Trample here. This is lecture number 18. Today's topic will be Faraday's Law. Well, during the first part of this course, we studied the electrostatic case, where we looked at the electric field created by stationary charges. The second major division of the course was magnetostatics, where we looked at the magnetic field created by direct currents, essentially. Today's lecture marks the beginning of the third section of the course, which is called electrodynamics. And what's going to happen now is we're going to allow both the electric field and the magnetic field to vary both spatially and temporally. They can vary both with space and with time. That's called the electrodynamic case. And when you allow that to happen, Maxwell's equations actually couple the electric field and the magnetic field. So clearly here, in one sense, you can see that the electric and magnetic fields are related here by Faraday's law. Similarly, the electric and the magnetic fields are related here by Ampere's law. And we still have the two divergence equations, the two Gauss's laws. A couple of important differences between the electrostatic and the magnetostatic case and then the electrodynamic case are as follows. While in the electrostatic case, we really only have and are concerned with the electric field, and in the magnetostatic case, we're really only concerned with the magnetic field. Typically, in the electrodynamic case, we're going to have both an electric and a magnetic field that we'll have to deal with, and they are going to be coupled again by Maxwell's equations as written here in differential form. I again feel obligated to point out just how general and how powerful these four equations are. They describe all macroscopic electromagnetic phenomena on scales all the way down to around tens of nanometers up to galactic scales where we're measuring things in terms of light years, distances in terms of light years. So they are extremely general and extremely powerful equations. Well, let's really dive into Faraday's law now and consider this in detail. So here it is. Faraday's law in differential form says that the curl of the electric field is equal to minus the partial derivative with respect to time of the magnetic flux density B, in a nutshell. We can play some games here by integrating the left-hand side of this equation over some area S. So that's what I've done here. Multiplied the left-hand side, or I should say taking the dot product of the left-hand side with some differential area and integrating. And doing the same, of course, on the right-hand side to preserve the equality. We can use Stokes' theorem on the left-hand side here. So the curl of the electric field integrated over an area, if you'll recall, is equal to the line integral of the electric field around a contour L that bounds that area, essentially. Okay. So it turns out that this line integral, the line integral of the electric field around a closed contour, is called the EMF, or the voltage, basically, around that contour. So we say that Faraday's law in integral form looks like this. The induced EMF around a particular path is equal to the line integral of the electric field around that path, which is, by this right-hand side of Faraday's law, equal to the integral over an area of the partial derivative of the electric flux density here with respect to time with a minus sign out front. This is Faraday's law in integral form, and you need to be familiar with both the differential form and the integral form. Well, as our first example here to see how we might use this, let's consider a stationary loop in a time-varying magnetic flux density, all right, or essentially a time-varying B field, all right. We refer to this sort of induced voltage as transformer EMF. Okay, so here's the idea. You take a loop of wire and you bend it into a circle like so, and allow a time-varying magnetic field essentially to penetrate the loop. And what Faraday's law guarantees is that so long as you don't bring this little straight part of the wire and this little straight part of the wire together such that you short them, so if you keep them separated, then there will be a voltage, a potential difference that develops between this side of the loop and this side of the loop at this point right here. And that's what we call transformer EMF. It's just due to the fact that Faraday's law says, okay, if you have a time-varying magnetic field throughout the area of the loop, then you're going to get a voltage that develops between opposite sides like this, essentially. Okay. All right. Now, a second B field also develops here due to the current I here, this red current that is induced by the changing magnetic field. So, not surprisingly, if you have a voltage that develops between this point and a resistance here, you're placing a voltage over across a resistor, then of course you are going to get a current that develops, and that current here is denoted by I. The B field, due to this induced current and the current that's induced by the changing impressed B field that we started with, we'll call B induced. And based on the right-hand rule here, if you stick your thumb in the direction here of the current, you can see that the field is going to wrap around in the direction of your fingers. And so the induced field, the induced B field is going to curl around the wire as indicated here by this figure. Okay. And again, this is just the EMF that develops between the voltage that develops between that wire and that wire due to this changing B field right there. That's due to Faraday's law. Okay, let's look at a second example. This is an inductor in a changing magnetic field. Okay, so here's the geometry now. Now we've got again, it's a time-varying magnetic flux density B, a time-varying B field that looks like this. There's some constant times 2y hat plus 3z hat. So if we're looking here in the zy plane, the field is tilted at an angle. So it's not at 90 degrees now to the plane of the loop, but rather it's tilted here at some angle. And it varies sinusoidally in time. All right. So again, it stands to reason that if we wrap a wire into a loop into a solenoid, we should expect that if we put a time-varying B field through that loop, it's going to again induce a current I. That's going to create an induced voltage, the VEMF here between the top and bottom of the loop of the solenoid. Okay, all right. Well, let's see if we can get an expression for the EMF here that develops between the top and the bottom of the loop. So we're assuming that each loop has a radius of A and that there are n loops. Okay. Well, the first thing we need here, if you'll notice, is if you ignore the time derivative here, what we really have on the right-hand side of Faraday's law is the flux of B through the coil. That's really what we're talking about. And so it's the same situation here. First, if we first find the flux, we can then take a derivative with respect to time and multiply by -1 in order to figure out what the EMF is. So let's just first find the flux of B through a single loop. Okay, that shouldn't be too hard really, because if you'll notice, while the magnetic field varies temporally, as sinusoidally essentially we would say, it does not vary spatially. It's uniform throughout space. That's going to make computing this integral fairly easy. So if we plug our this expression for B into this integral right here, we end up in this situation, which is B dot ds integrated over the area. Now recall that ds is going to be normal to the area of the loop, essentially. So it's going to be normal to the cross-sectional area. So in this case, ds is going to point only in the z direction. So what's going to happen is we're just going to pick out the z component of the B field, and we're going to multiply it because it's constant over the entire cross-sectional area of the loop. We're going to multiply that that magnitude 3 here of the z component of the B field times the area of a single loop, pi a squared, times the constant B naught times sine of omega t. That is the flux of B through a single loop. Okay, now remember, in order to get the induced EMF by Faraday's law, we have to take a derivative with respect to time. So let's do that next. And since we have n loops, the flux gets multiplied by n, essentially. So we take the derivative of this expression with respect to time. That just, the omega pops out front, and we have a cosine. Derivative of sine is cosine, and then Faraday's law says we need a negative sign out front. So there you go. This is an expression, and it does depend on time. It's a time-varying expression for the voltage that will develop here between the top side of the loop and the top of the solenoid and the bottom of the solenoid. And again, just like before, though it's not denoted here, because you have an induced voltage here, you'll also have an induced current. That induced current will have its own magnetic field that will also penetrate the loops. Okay. On that note, let's talk a little bit more about the nature of the induced B field. Okay. Just to state this as succinctly as possible, the polarity of the induced EMF, and therefore the direction of the current, is determined by Lenz's law, which states that the induced current in the loop is always in a direction that opposes the change of magnetic flux psi of t that produced it. Okay. What does that mean exactly? Well, let's look at this diagram here. We have an impressed B field from some external source here that is penetrating our loop, and the impressed B field is pointing in the plus z direction. All right, so there is flux. You can think of it in this way. There is a positive flux due to the impressed B. Okay, the impressed B field. Now, as we mentioned before, there is an induced current here that has its own magnetic field that produces an induced B field like so. And we figured out that if we put our finger in the direction, or our thumb in the direction of the current, our fingers wrap around in the direction of the field. If you'll notice, however, though, the direction of this induced B field over the area of this loop is in the opposite direction of the impressed B field, B of t. In other words, the impressed B field is pointing up. Let's look for instance here in the center of the loop. The impressed B field is pointing up in the positive z direction. The induced B field is pointing down in the negative z direction. That's a consequence of Lenz's law, which says that if you are producing a flux, a positive flux, if you want to think about it in this direction, whatever current is induced by that positive flux is going to have its flux in the opposite direction. Okay, so in other words, its flux is going to be negative essentially in this particular case. All right. So again, the polarity of the induced voltage and therefore the direction of the current is determined by Lenz's law. So again, if I didn't have this current labeled on here, I could figure out what direction it was in simply by looking at the direction of the impressed B field, B of t. Since I know that it's positive, I know that whatever current exists is going to be opposing, is going to create a magnetic field in the opposite direction, in the minus z direction throughout the loop. Therefore, based on the right-hand rule, in order to get a field to do that, I need to have the current flowing as indicated here by these red eyes. Okay. Let's look at an example here for Lenz's law. Here we have a time-varying impressed B field here again. B of t is minus 0.3 t in the z hat direction. Okay, so it is pointing in the negative z direction. It's pointing downward. Okay, that's what's sort of being indicated here. So this is an indicator that the B field shown here in green is directed in the negative z direction. So x means into the screen in this case. All right. Well, we know that around this loop here, there is going to be we know that around this loop there is going to be a voltage that develops because this magnetic field is varying with time. What we would like to know is what is the voltage that develops around the loop, or equivalently, what are the voltages dropped across the 4 ohm resistor and across the 2 ohm resistor. Okay. In order to do that, in order to figure that out, we need Lenz's law, okay, and Faraday's law specifically, but also Lenz's law. Let's just look qualitatively here and see if we can reason through and figure out what direction the induced current is going to be just simply based on Lenz's law. Okay. Well, we know that the impressed B field points in the minus z direction. So whatever direction our current is in, it needs to create a field throughout the loop that opposes that. In other words, that points in the plus z direction. So I think you can convince yourself that if the current is flowing in a counterclockwise direction like this, if you put your thumb in the direction of that current, then your fingers curl around in the direction of the current. And if you put your, again, if the current is flowing in a counterclockwise fashion, then the induced B field will be in the plus z direction. That's what's required here by Lenz's law. So we know we're going to get a positive voltage drop like this in this direction, plus to minus like that, and then here plus to minus like that because the current is flowing in a counterclockwise way. Now the question is, what is V1 and V2? For that we need Faraday's law. Proceeding as before, we need to figure out, okay, what's the flux of B throughout this loop? Very similar argument as before. In this case, the field is only directed in the z direction, and again does not vary spatially. It's constant spatially. So when we do this integral here of b dot ds, ds points in the plus z direction. It just simply picks out the z component here, and all you have to do is multiply by the area which happens to be 4 square meters. 4 times 0.3 is 1.2, and we get an expression for our flux psi of t, which is equal to minus 1.2 times t. All right, well, how do we figure out what the EMF is? Well, remember, we have this little equation, which is that for a single loop, the induced EMF is minus 1 for one loop times the time derivative of the flux. So in this case, flux is negative, time derivative of 1.2 t is simply 1.2, and the induced EMF here is equal to 1.2 volts, right? That's the total voltage induced all the way around the loop, all right? However, that total voltage of 1.2 volts is distributed across a 4 ohm resistor in series with a 2 ohm resistor, okay? So we know the total current then, the total current is going to be the induced EMF divided by the sum of the resistances because they're in series, okay? Remember, this voltage, the EMF, is that which develops between two closely separated points all the way around the loop, essentially. So if we were to hold if we were basically to split the loop, keep them from touching, then in between those 2 points there would be an induced EMF, okay? And that is going to be dropped across both of these resistors in series. Okay, so that way we can use Ohm's law then to figure out the current, which is just the voltage divided by the sum of the resistors, 0.2 amps. Once we know the current, then it's easy to find the voltage dropped in this direction. That's just IR, 4 times the current here. For this one, 0.8 volts is dropped across the 4 ohm resistor, and 0.4 volts is dropped across the 2 ohm resistor. So that problem is a combination of Lenz's law. We need Lenz's law in order to figure out what direction the current is, and therefore the polarity of those two voltages. And then Faraday's law. We needed Faraday's law in order to figure out what the induced EMF was in this case. Okay, well, the most general case that you can have is a moving loop in a time-varying B field, okay? And interestingly, there is a contribution to the induced EMF due to the motion of the loop. That's captured by this term right here in this equation. And there is simultaneously a contribution to the induced EMF around the loop due to the fact that the B field is time varying. That is captured by this term in the equation. The total EMF is the linear sum of the two. All right. So let's try to figure out, okay, what is the EMF induced around a coil, or sorry, a moving loop in a time varying field. All right. So let's say that the B field has this form. It varies both in terms of space, like this. It's a function of y here, and it also varies temporally as a function of time. All right. It does point, however, in the plus z direction. So if positive x goes down like this, positive z is out of the screen. All right. And simultaneously, let's say that just one side of the loop is sliding down sort of these two rails here with a constant velocity of 20 meters per second. So that's what u is. So our task is to figure out, okay, what is the total voltage induced around this loop as a function of time due to a B field that varies in time and a loop that is itself moving. Okay, let's first work on this term of the equation. Try to figure out what the EMF due to the time varying B field is. Okay, well, here we go. This is our the first term in our equation. We know that the derivative of B with respect to time is going to give us this expression here. We take the derivative of this cosine term with respect to time. Derivative of cosine is minus sine. And we further have to integrate that over the area of the loop. Well, the area of the loop is changing with time, right? Because this side is sliding, this area right here is changing with time. So what we have to do in order to deal with that is integrate the x coordinate from 0 to 6 centimeters because, let's see here, because this side is 6 centimeters long. That doesn't change with time. So we just integrate over that x from 0 to 6 centimeters. That's what we were doing here. And then we're integrating over the y direction, this direction here, from y equals 0 up to y. All right. In order to do that, we introduce a dummy variable y prime over which we're going to integrate. So we're integrating from 0 up to y. We're integrating y prime, I should say, from 0 up to y. Recall that, again, this B field depends on the y coordinate. So it's not constant spatially in this case. So we introduce a dummy variable y prime, and we integrate that dummy variable from 0 up to whatever position y the right-hand side of the loop currently is at. So here's the integral that we have to deal with. And again, it's not a difficult integral. The integration over x just gets you a factor of 0.6, and the integration over y gets you this cosine 10 to the 6t minus y prime term. We evaluate that from 0 to y. And this is an expression then for the EMF due to the fact that the B field is varying with time. We had don't get confused by the fact that we had to take into account that the area is also changing with time. Really, if this B field was not time varying, we would not see an EMF from this. So we think of this as the EMF due to the time varying nature of the B field. Okay, now we need the second term in this equation right here. This is called the motional EMF, the integral over L of u cross B dot dl. Okay, well, here's the u term, 20 y hat, that's equal to u. And this is B right here. So we have to take, formula says, u cross B dot dl, all right? Well, and technically, you have to do this all the way around the loop, over all four sides. However, 3 of the 4 sides are stationary, and therefore u is 0 on 3 of the 4 sides. So u is 0 here, u is 0 here, and u is 0 here. Therefore, we only have to integrate really from this point to this point right here along this side, where u is non-zero. U is equal to 20 meters per second in the plus y direction. Okay. So that's what we're doing right here. We're integrating from 0.6 up to 0 in the x direction along that side that's sliding, u cross b. So when we take the cross product here, u cross b, y cross z, that's going to give you a minus x, okay? And then you're going to dot that with dl, which is in the x hat direction, dx x hat, this is dl. So all we've done here is set this integration up, u cross b dot dl. Okay, so y cross z, that gets you a minus a minus x. Let me think for just a second here. X, y cross z, that gets you a plus x, excuse me. So y cross x gets you a plus z, and then we're going to be integrating here with respect to x. That gets you a factor of 0.06 out front. The minus sign has to do with the fact that we're integrating from 0.6 up to 0 rather than 0 to 0.6. Okay. So multiplying those factors together, the motional EMF is right here. This is the motional EMF. The total EMF is simply the sum of the two. The first EMF plus the second EMF. Now notice that the first EMF, due to the time-varying B field, is huge compared to the motional EMF in this case. The side of the loop is just not moving fast enough to induce very much voltage. So this is down here on the order of millivolts, excuse me. And so the motional EMF is on the order of millivolts. The other EMF, the time-varying EMF, is on the order of 240 volts. So, again, you've got several orders of magnitude difference. But nonetheless, the point being, the time-varying EMF causes a motion. The time-varying B field causes an EMF, and the motion of the loop also causes an EMF. And the total EMF is simply the sum of the two. Okay, that's it for this lecture. Thank you for your attention, and I'll see you in the next one.